Previously, a stream of works focused on the reconstruction of inhomogeneous instances like flames, gas flow, fluids, cloud, and so on. Differently, what we consider is all about solid transparent objects. Actually, for solid transparent objects, there already exist some intrusive approaches for reconstruction. The most direct method is to paint and then scan. Others may consider to immerse their target objects into liquids. Then it is possible to infer the geometry using the laws of physics. But an obvious drawback of this kind of method would be immersion itself, because it is not so suitable for some precious objects. In comparison, our method is designed as a kind of non-intrusive method. Recently, inspired by the law of refraction, people started to investigate the relation between geometry and refraction properties, like measuring the light ray paths traversing through the objects, and then recovering the surface by optimization. So based on this, here we first introduce a recent work published in CVPR 2016. This is the basis of our work. Suppose we have already captured the ray correspondences by the camera, which means the relation between the very first ray that enters the object and the last ray that exits the object, marked as red arrows in this figure. Then by backtracing the rays, we could find two intersection points with the pre-assumed object, denoted as P1 and P2 here. If there only exist two refractions, after connecting these 2 points, it will generate a complete light ray path. By computing the surface normal and the Snell normal at each intersection point, we could then formulate an optimization that constrains the consistency between these two different normals. After optimization, the intersection points will be updated to satisfy the law of refraction more closely. By the way, because of the limited viewing angle of the camera, the recovered point cloud will only cover a part of the object, like the front and back region in our example. So, in order to reconstruct a full shape of an object, a straightforward method would be to capture ray correspondences from different views and then use optimization mentioned before to generate a point cloud. Later, we tried to directly merge all the pieces together and do the reconstruction. But as you can see, the result is misaligned and very noisy. In contrast, here is our method. We started from an initial model, and then it will be optimized gradually to achieve a satisfactory result after several iterations, with necessary geometry details recovered. Compared with the ground truth, as visualized with pseudo-color map, the average distance from the reconstructed model to the ground truth decreased obviously as expected. So therefore, the final result is better. We first introduced our automatic capturing setup. By positioning the transparent object on a turntable, the object will be rotated and observed in different viewing angles with respect to the camera. The monitor will simultaneously display gray color patterns. The system works like this. After capturing, we pre-process the captured data and compute ray correspondences and the silhouettes of the object of the different viewing angles. Then, we start the optimization from an initial model generated by shapefront silhouettes. We apply normal consistency mentioned before to obtain optimized point clouds at the beginning. Then, we propose two novel point consolidation methods to refine those points, followed by Poisson reconstruction to reconstruct a 3D mesh. After several iterations, the whole algorithm will output the final reconstruction result. Next, we will focus on two consolidation methods. The first one is surface projection. As illustrated before, the directly merged point cloud is very noisy and misaligned as shown here. A straightforward idea would be denoising. What we use here is WLOP, a robust denoising algorithm proposed by Huang in 2009. We changed the only parameter, radius, in our example. It turns out neither a small radius or a larger one is suitable. The result is noisy or over-smoothed respectively. On the other hand, we observe that since we have an initial model, the samples on initial model must be complete but kind of inaccurate. We also have optimized point cloud that satisfy the law of refraction, so it is relatively accurate but incomplete. So does there exist a method that could combine these two in order to generate a complete and accurate point cloud? We propose an adaptive radius-based surface projection algorithm to achieve the goal. As you can see, after optimization of the previous step, the concave regions on the surface is better captured by the optimized point cloud as marked green here, compared with the samples marked as green here. Instead, the convex region could be well estimated by both points. So we consider to use an adaptive radius to project the samples on initial model marked as A here to the optimized point cloud B. As shown here, a larger radius should be used when the samples is far away from the optimized point cloud, while a small radius is preferred when they are close. After projection, the reconstruction is much better than before, with much more details recovered. Here is the math behind this. We try to minimize the distance between A and B with controlled radius, which is enabled by a descending function here. The effect of this function is determined by an adaptive radius. So for more details about how to compute it, please refer to our paper. In order to have a more intuitive understanding, projecting sample points using adaptive radius results in a consolidated point cloud in red here that better captures the shape of the kitten around its ear and back, while maintains to be smooth. So please see the cross-section curves shown here. Okay, let's check the pipeline again. Since we can output a complete and a smooth point cloud now, thinking that if we remove the second part from the algorithm, what will happen? After 25 iterations, we plot the average distance of reconstructed models and the ground truth. We can say the improvement is not very obvious. Here is an example of the result from 20th iteration, rendered as transparent blue compared with the ground truth. The ear and the tail region is far away from the satisfactory. The reason here is there may exist multiple possible surfaces that could satisfy given array correspondences, like surface 1 and surface 2 here. Actually, if the initialization of each step of the optimization is not very good, the result could be stuck in a local minimum and get worse. Based on this observation, we propose to say that consistency constraint. After previous step, we first project the point cloud onto the image